All right, folks, the last set of notes, last lecture in Chapter 8, the payoff. This is so cool. Here's what we're going to do. We're going to bring together the idea of intermolecular forces and physical properties and how they're correlated. So here's the what was I going to say? Payoff, summary, conclusion, I guess. When the intermolecular forces are stronger, more or less energy is required to separate the particles. More. If they're more sticky, if the force attracting them is stronger, it takes more energy to separate them. Conversely, if I have relatively weaker intermolecular forces, less energy is required to separate the particles. And now look what we can do. Now, we didn't talk about surface tension, viscosity. Just because we didn't have time to cover everything this semester. Weren't able to cover everything this semester, let's say. Viscosity, think about, this isn't a very good example chemically, but physically it makes sense. Think about trying to pour honey. It flows very slowly versus pour alcohol or something. Rubbing alcohol is a pretty good example. Alcohol has very low viscosity. It flows easily. Honey, which is a mixture, has very high viscosity. Surface tension, I think I can do. Look at this. Now, we know that things float if they weigh less than water. Specifically, or more accurately, if they're less dense than water. So, of course, there's a paperclip. It's metal. Density might be 6, 7, 8 grams per milliliter. Water is 1. So, of course, it just sinks right to the bottom. Unless you've had Chem 51. If you've had Chem 51, you might be able to pull off this trick. That's heavier than water, meaning more dense than water. And if I put it down on there, giddy up. Check that out. That's surface tension. You've seen like those water strider bugs that skim across the top of the water. That's surface tension holding it up. Could I zoom in? I want to try zooming in. Now that's a little bit difficult to see, but maybe as it sort of rotates around, there's like a skin on the water almost that's supporting that paperclip. I'm going to see if I can even zoom in a little bit more without wrecking everything here. It's sort of like, I'll move it around. There's like a skin on the top of the water. That's surface tension. All right, so let's go back to page 8.21 and make some notes about that. Isn't that cool? Now you can amaze your family that's home with you, bored to death. You can say, I'll float this on water. It's not floating. It's sitting on the sort of surface tension effect. Okay, so we can say when the intermolecular forces, interparticle forces, are relatively stronger, surface tension is higher. Viscosity, we didn't really talk about, but it's higher. Vapor pressure, now think about it. It's harder to separate the particles. It's harder for the particles to escape into the gas phase. Well, wait a minute. That means if the intermolecular forces are stronger, vapor pressure is going to be lower. The boiling point, how high, how hot, how much particle energy do we need to get them to break up? It's got to be higher. Melting point, how much energy do we need the particles to have to separate? It's got to be higher. Heat of vaporization, how much energy do I have to put in to get those atoms or particles to leave the liquid? It's got to be higher. And again, how much energy did I have to put in to get the solid intermolecular forces to sort of break up? It's higher. Now there's a couple of tricks here. Boiling point is a temperature. Melting point is a temperature. Heat of vaporization, heat of fusion is typically, well, we'd say calories per mole or per gram, or we could say joules or kilojoules per mole or per gram, something like that. It just becomes a regular conversion unit. It's no big deal, but so this is sort of the amount of energy per gram, amount of energy per mole to get them to go at the boiling point to vaporize, at the melting point to break up and become a liquid. Now we have some examples where I'm saying these are stronger and weaker. So I'm going to go through and compare these. And I look here and I go, oh, well, I've got hydrogen bonding right here. Here I only have dipole-dipole. So hydrogen is going to have, water is going to have higher surface tension, higher viscosity, higher boiling and melting point, heat of vaporization, heat of fusion relative to H2S. But it's going to have lower vapor pressure relative to H2S. Now you might try that, go through here and say, well, what kind of interparticle forces here, make them relatively stronger, weaker, have these properties, relative properties, or these relative properties. So you maybe stop the video, go through those. All right, you stopped it and you sorted it all out, right? Well, I only really needed one column here, but we could say, well, if I thought about relatively weaker intermolecular forces, these are all lower and higher. Relatively stronger intermolecular forces, these are all higher and vapor pressure is lower. It's the same thing, just converse. Okay, let's look at NaCl. That's chapter 3. We know those are ions. Sorry, I couldn't hit pause soon enough. Those are ion-ion. Over here I've got dipole-dipole. Here, so stronger, weaker. Here I've got dipole-dipole. Here I've only got London dispersion. Now that doesn't make sense. You might want to draw those little structures and think about it. Now wait a minute. Here, both London dispersion. No ions, no hydrogen bonding, no polar molecules. We've said, chapter 4, hydrocarbons are nonpolar. So you're like, well, wait a minute. How do I sort those out? Oh, more electrons, fewer electrons. And that's often the way London dispersion works. It's the tiebreaker. If everything else is the same, you go to London dispersion and say, well, who's got more electrons? Same thing here. Same thing for argon. More electrons, fewer electrons. So that's the payoff. This is a culmination of everything really important that we've done in chapter 8. 8.22 has some applications. Now, boiling point increase or decrease. So is the intermolecular forces going up in this list or intermolecular forces going down in this list? Atoms and nonpolar molecules, they're all London dispersion. Nothing polar, no hydrogen bonding, no ions there. So all I have to do is look at the number of electrons. 36, 18, 10 electrons. That's decreasing boiling point. Try this one. Stop the video, do this one. These are pretty easy. Stop the video, do that one, decide if it's increasing or decreasing. All right, you sorted that out. What have you got? Like 14 electrons, 18 electrons, 54 electrons. So that's increasing boiling point for that set. Here's an awesome example. I love this one. I have 3 molecules that are pretty similar, mostly hydrogen and carbon. But I have to kind of go back and draw chapter 4 and say, well, wait a minute, can I draw this and this and this and this? Well, that's a little bit weird, but the only way you can reasonably draw that thing, right? It says CH3, that hints at that. CH3, H, that kind of hints at that. And there's an oxygen in the middle. So acetone is polar. Ethanol, CH3, CH2. Who's the idiot that did this? 2. Well, you start thinking about the Legos. Oh, CH3 and a CH2 and an OH. Oh, yeah, that sure looks like hydrogen bonding to me. So I'm going to say this is going to be dipole-dipole. This is going to have hydrogen bonding. Here's a hydrocarbon. Not polar, no ions. That's got to be London dispersion. And I've got another hydrocarbon over here. London dispersion. So highest intermolecular or highest heat of vaporization is also the highest or strongest IMF. Lowest is the weakest IMF. Well, the first one's kind of easy. I go, well, I've got hydrogen bonding there. Ethanol. CH3, CH2, OH. I go down the list. Oh, there's London dispersion, acetone. Wait, did I say London dispersion? Dipole-dipole. Hydrogen bonding. Well, now I've got this little C1 hydrocarbon or C3 hydrocarbon. C3 hydrocarbon's got more electrons, so it must be propane and methane. If that doesn't make sense, sort of stop the video, go slower. I'm trying to go quick so I don't make these files that tie up whatever device you're using. Here, why don't you try this? It's problem 109. I tweaked it a little bit. Try that problem, stop the video, try that problem, and then come back and see what my conclusion was. Okay, my conclusion is I've got a boiling point of almost 200. That's a much higher or stronger IMF. I've got something boiling at 3 degrees. That's the weaker IMF. So I'm going to go here and I say, oh, well, there's hydrogen bonding. In fact, ethylene glycol has got 2 OH groups or HO groups. Chloroethane looks all nonpolar. Oh, wait, there's a chlorine sticking off one of those carbons making it polar. So dipole-dipole, hydrogen bonding. This must be the 198 degree boiling point, and this must be the 3 degree boiling point. So you can see those are very similar number of electrons, similar molecules, but a huge difference in the physical properties. All right, let's look at page 8.23 and see what we've got. Okay. Lowest to highest. So strongest, weakest intermolecular forces to strongest intermolecular forces. Now I'm going to do this. I'm going to pick out that. Lithium fluoride. Ion. Then I look through here. Chlorine, fluorine, HCl, HF. Oh, HF. Why? Stop and think about that. Hydrogen bonding. HCl. Dipole-dipole. Now I've got to pick between fluorine and chlorine, but you're getting good at that now. You're like, oh, fluorine's got fewer electrons. Chlorine's got more electrons. London dispersion. Bingo. Melting point values. Lowest is the weakest intermolecular forces. Highest, strongest intermolecular forces. I'm going to say H2O is the 0 degree hydrogen bonding. Now, if I were to draw those two molecules, they're both polar. There's kind of a hydrogen stuck, two hydrogens at about 109 degrees apart or so from the selenium and the tellurium. So you're like, okay, wait, they're both dipole-dipole. Well, we're going to go to London dispersion forces as the tiebreaker. I calculated 36 electrons for H2SE and 54 electrons for the H2TE. So I've got to sort out those two numbers. This one is going to have higher, so H2TE minus 48, H2SE minus 86 degree boiling point. Now it gets a little weird because you're thinking, well, wait a minute, is this higher or lower? So you might stop the video and think, oh yeah, mathematically, lowest, next, highest. Just looks a little weird with the negative values. Same thing here. I would suggest you stop the video and say, okay, wait, these are going up. What does that mean about intermolecular forces? How can I sort out what I have here to match that? So stop the video, see if you can sort that out. All right, you're back. So you said there's hydrogen bonding and everybody else is dipole-dipole. So you probably said, okay, I'm going to put HF there because of hydrogen bonding. Then these are all dipole-dipole. Fewest electrons, more electrons. Stronger intermolecular forces. They're all dipole-dipole, more electrons. So we'd do what? We'd go HCl, HBr, HI. All dipole-dipole. Again, same thing. All dipole-dipole. All I'm going to do then is count the higher electrons, stronger intermolecular forces, higher boiling points. So now you can probably just go, oh, that's F2, Cl2, Br2, I2. Again, here's my delta H. Remember I said these are not temperatures. There's some sort of energy per amount. So this must be F2, this must be Cl2, and that must be I2. Now, I went through that fast. Again, I'm trying to not make these huge files. But you're going to go back and go through those. And well, wait a minute now. Why exactly did he do that? And here's our last page. It's the summary. It's different than what we've done in the past because what we're doing this semester is different than what we've done in the past. But the first thing we did was we looked at gases, really only to think about what their particles were doing. So pressure is the particles bouncing off the walls. So we could say particles colliding with walls of container. That's what pressure is. Temperature, we said, now this is a little bit of a fib, but it's okay for Chem 51. It's related to the speed of the particles. It's more complicated than that, but that's okay for Chem 51. Temperature and pressure conversions, maybe a couple, not a big deal. You're going to see millimeters of mercury, medical people, and we're going to see PSI, maybe atmospheres. So, there were a couple problems in the homework where you do those conversions. Here's our IMFs. That was the next thing we talked about. Now, this chapter doesn't really have ion, but really that was chapter 3, and it kind of goes with what are the forces holding the particles together. Ionic compounds. We see an ionic compound, they're really strong interparticle forces. They're ionic bonds, so very, very strong. Then we kind of looked at the things in this chapter and we said, well, then we go hydrogen bonding, a lot weaker, but the strongest of the weak forces, dipole, and then London dispersion. Well, hydrogen bonding, we look for molecules that have OH or NH. This is sort of rare, but FH. So as soon as I see a molecule with that or something like that, that's how I recognize hydrogen bonding. So these are molecular compounds. I'm drawing molecules, so molecular compounds with that. Dipole, I'm looking for polar molecules. So we're back at like chapter 4, polar molecules. London dispersion, nonpolar molecules. Nonpolar molecules or atoms. So those are all implying compounds, ionic compounds, molecular compounds, and atoms fit into that London dispersion. Here they are. Weakest, London dispersion, dipole, hydrogen bonding, ion. This is what we were doing in the last section, saying like, well, what about melting and vaporizing and boiling and all that stuff? What are the particles doing? And then here was what we just did today. We said when the IMFs are stronger, things like the melting point increases, the boiling point increases, the amount of energy required to melt increases, the amount of energy required to vaporize or boil increases. And we didn't do much with this, but surface tension and viscosity. I don't think that shows up in the homework anywhere, but it all makes sense. Now there's one oddball. When the IMFs are stronger, vapor pressure drops. Everything else goes up. All the other physical properties we looked at, the values go up, vapor pressure goes down. And we're not really doing this semester because, we just don't have time. All right, chapter 8 I think is really cool. Now, I know I say that every chapter. Chapter 8 is cool because we can take those little things we know and start making these kinds of predictions based on the little bit that we know. We can make physical property descriptions. The next chapter is chapter 9, which is solutions, a completely different animal. We're going to mix things together and then talk about how those behave and how we sort of deal with them in practical ways. All right, thanks for hanging in there, folks. Only 2 more chapters to go. Bye now.